This is pretty exciting. This is the first reaction, I think, where you will be able to tell exactly what every single valence electron is doing from the start of the reaction to the end of the reaction. It's an alkene reaction, and we've talked about addition reactions, and it's electrophilic because the alkene is attacking an electrophile, a species that is partial positive. This is the first reaction for the semester. We're going to see around 35 once everything is completed. The key point for this first reaction is a pi bond is considered to be electron rich, and it can act as the nucleophile. In other words, it is the attacker or the electron source. Same thing. We've labeled this reaction RxN 6A or reaction 6A. The way that I learn reactions is I learn to verbalize the reactants and the product. I have in my mind a general, not a general, but a representative reaction. And I have a couple of very important notes about the mechanism, something called the regioselectivity, and something called stereoselectivity. And we'll get to those two terms a bit later. But try to follow what I do here. We're going to take an alkene and react it with HBr. It could be HCl, it could be HF, it could be HI. X is just a halogen. And in this particular case, the product is this. The three carbons are exactly how they look in the starting material. We take off the double bond and we add Br at this position. Okay? Everything, all the carbons stay exactly where they started. There, and there. 4 carbons. 1, 2, 3, 4. For this reaction, you will be expected to know the mechanism completely. And again, we'll go over these two terms as we get to them in the mechanism. The idea here is that I'm not going to give you a blank page for the mechanism, but instead you're going to draw this in your notes. And I'll do the same thing here. Alright, we're taking an alkene, reacting it with ch6, giving us an alkyl halide. Alkyl halide. Let me show you exactly what happens in this reaction. When you draw a mechanism, redraw the starting material, and particularly draw the starting material or starting materials that participate in that first step. This is something that you will have to memorize. If you're having trouble memorizing mechanisms, come see me in office hours. Most likely we will go through the process drawing out all the carbons and hydrogens using Lewis structures, and then we'll transfer or transition into line structures. Drawing mechanisms is a bit of an art form. You want to make it very clear to the reader that you know what's happening to every bond being made and every bond being broken. So I am going to draw that bond between H and Br. You don't do it here if you're just showing the general, sorry, not the general, we'll call this the overall reaction. Alright, you've seen this mechanism before. The pi bond attacks a hydrogen, kicks out bromine. All of these words are important. So, I don't write everything that's important, but you'll hear me over and over again. Pi bond attacks, kick out a leaving group, or kick out, in this case, a bromine. Now, this is very tricky, because if you go to another source will teach it maybe somewhat differently. We could be both right. It's just a preference. For instance, some professors like to draw an equilibrium arrow here. technically it is equilibrium, but there's always a gray area. And I think this happens in appreciable amounts that we will just draw a regular arrow. And here we have a plus charge. Again, if you're not very clear why, based on the mechanism arrows, then come to office hours, and what we'll do is we'll draw these as Lewis structures. But I think for most of you, you see this a lot more easily. Okay, and we kick out a bromine, or not bromine, but bromide, the anion. Okay. The next step, pretty easy. Opposites attract, negative attracted to positive, source of electrons, electron deficient. And this is the last step. And I will draw it to the right. You could draw it down if you ran out of room. And we have this. Okay. So what are some key features? That is the answer. If I ask you to draw the mechanism for this particular reaction, this is the answer. But what are the particulars? The particulars are this. First of all, you form the more stable carbocation. You notice that I don't draw the minor carbocation. Okay, so this is a more stable carbocation, not, what was the other option? The other option was to put the hydrogen on the middle carbon, the plus charge on the end carbon. But you would realize that this is primary. This carbocation is tertiary. Okay. So again, what the answer is written in blue and pink. Green are my notes to help you learn the mechanism and hopefully memorize it. And let's see. I think that's it. You know, you could think of, I like to memorize the first step so I don't get stuck. I immediately know the first step, and then after the first step, you know, that gets the ball rolling, and maybe once you see the products of the first step, you know what to do next. It's pretty obvious. You have opposites attract. But the first step here, how are we going to describe this? Pi bond attacks H and HBr, and you kick out the Br. Why is this the case? I said pi bonds are electron rich, or you should think of them as electron rich. This bromine is partial negative, electronegative, right? Rendering this hydrogen partial positive. That's the opposites attract. Electron rich, electron poor. Okay. Let me just make sure there's nothing else I want to say for here. Okay. Now, there's oh, by the way, the last thing here is I'm analyzing the possible stereochemistry of the final product. But this molecule is not chiral, it's achiral. Why is that important? Because I may ask you, draw all the products if you made a stereoisomer, or if you made a chiral molecule that can exist as R or S. This is not the case, right? This carbon is neither R nor S because it is not a chiral carbon. So this is the product. You should not be drawing wedges and dashes. You should not be drawing multiple products in this case. As you could probably tell, these reactions from here on out are very case specific. If you try to memorize just this and only this and not know how to apply this to other molecules, other alkenes, I can't even imagine how difficult that would be. Okay, you really need to understand what's happening in the mechanism. The other last thing, and then we'll get back to the handout, is that you want to draw all the products produced at each particular step, or each, at each step. What does this mean? It doesn't mean that you draw all the final products at each step. It means that you draw exactly the products that occur at each step. So here I do produce a Br minus, and I have to draw it. Here I do produce a carbocation, and I draw it. That's fine. I mean, I think that's convenient because you have these two react with each other. But there'll be times where you're drawing molecules that are a result of the previous step that are not used in the next step. I think when we get to more examples, you'll see what I mean by this. And I'll point it out. I'll point out that I am drawing every single product of that particular step. And I'm going to put the word particular. Okay. Just store that away in your mind, and we'll see later what I mean by this. Let's go back to the notes, because that idea that we are putting the bromine on the middle carbon and not the end, that idea was elucidated by Markovnikov, a Russian scientist, about 125 years ago. The other thing that maybe I could put here, you wouldn't put this as an answer, but as a reminder, since we're first learning this reaction, is we don't get the constitutional isomer this on the other carbon. That is a possibility, but we've rejected it because this is actually coming from the less stable primary carbocation right there. Okay. All right. Now that difference where we choose this and not this, that is called regioselectivity. You're choosing between two constitutional isomers. You notice that these are constitutional isomers. Now, if we were choosing between two stereoisomers, or like two enantiomers, then it would be stereoselective. Let's not worry about stereoselectivity right now. Let's worry about why the bromine goes on the middle carbon and not this end carbon. The other thing is, I should have mentioned this way at the beginning, these are addition reactions. So you're adding something to each each carbon of the double bond. So this is important. Does the H go here, or does the H go here? Does a Br go here, or does a Br go here? You did realize that, correct? That this molecule, that H is now on this carbon. This carbon got something, and this carbon got something. Both carbons get something. You have to decide where the hydrogen goes. Well, like I said, Markovnikov developed this rule that tells us about the regioselectivity. And we could say that the regioselectivity follows Markovnikov's rule, which is this, down here. The H and the halogen add in a Markovnikov fashion. And what does that mean? I'm going to give us the saying, the rich get richer. And the money is hydrogen. What does that mean? Take a look at this starter material that we have here. Which carbon is richer in hydrogen? This one or this one? See, this carbon has one hydrogen. This carbon has two hydrogens. This is the richer one. So when you're adding HBr, the rich get richer. And maybe I should say that. I'll write it as rich. This is the rich carbon because it's richer in hydrogen. This is the poor carbon. The rich get richer. Well, take a look at the product. Did the rich get richer? Yeah. See, this carbon has two hydrogens. Now it has three. The other carbon gets the bromine, the one that was poor. This is just a mnemonic. I kind of doubt that Markovnikov actually said this in Russian, but I think this is, this is one way to remember what Markovnikov's rule is. There's other ways, and I think you'll develop your own way when you see more examples. So, from the mechanism that we have right here, if you're an audio learner, verbalize what happens, right? You start with an electrophilic addition where you add the H atom from ch6 to form a carbocation. I call this the rate determining step. The rate, we talked about this a little bit in class. Determining step is actually a term you've heard in general chemistry when you were doing kinetics. It's a slow step. Okay, but we're not going to do any equations that talk about kinetics. We just have to know which is a slow step. So I'm going to label it here. This is the RDS. Typically with alkenes, the RDS is when the double bond attacks. So it's typically the first step, the slow step. Okay. And then, as we verbalize this mechanism, we could say that the more stable carbocation is formed. Okay. Oh, here's something new. The hydrogen can add from either side. What do I mean by that? That alkene is flat. So this hydrogen can come from you can think of it as the front or the back. But also this carbocation is flat. So the bromine can come from the front or the back. The thing is, it doesn't matter front or back because the molecule has no chiral carbons. You only actually observe it in a model or by X-ray spectroscopy if the molecule has a chiral carbon. Then front and back will give you something different. But here, front and back, it's the same molecule. You could literally make this molecule have the Br in the front, and then make it again have the Br in the back, and they are identical. Hence only one product. So we'll talk more about this idea of stereoselectivity. It is not stereoselective. Okay, it doesn't matter. It is not stereoselective. What that means is, I'll give it away, it's a 50-50 mixture. If the carbon is chiral, okay? If it's not, then it's just 100%. Looks like that. Again, when we get to more examples, this would become abundantly clear. The last step is the halide adding to the other carbon, right? Opposites attract. This is only a two-step reaction. And since the halide is adding to a carbocation, again, we could get from attack from either side. Again, don't worry about this stereoselectivity. We will talk about that probably in the next page, in the next video. So in the last minute or so, let me show you how to draw these products pretty fast. We're not going to worry about wedges and dashes. We're not going to worry about R and S. So this is the easy part. No wedges and dashes. So here, okay, it doesn't matter if we add it to the carbon on the left or the right, because it would be the same molecule, okay, if we're not worried about stereochemistry. How about here? The rich get richer. Oh, by the way, both of these carbons are equally rich. They both have one hydrogen. The rich get richer. At some point, you don't even have to say that to yourself. You will see a pattern. For this ring, both carbons are equally substituted, so it doesn't matter which carbon, right? Again, if you're having trouble, I'm choosing between these two, and these two. But it doesn't matter for the first and third because it's symmetrical. Those carbons are equally substituted. But look at this next one. Choose between that and that. Okay? The rich get richer. The hydrogen goes here. The chlorine goes there. And then the last one, we have these two carbons to choose from. That's the richer in hydrogen, so the iodine goes there. What is the pattern? If you can figure out a pattern, I like to say the richer gets richer, but I have to remember that means for the hydrogen. But other people, when they see this pattern, you see what else you can say about where the halide goes? Where does the halide go? The halide goes on the more substituted carbon. So that's another trick. There, more substituted. There, more substituted. There, more substituted.